Okay, as you can see, this is the video for the 2017 AP Calc AB free response 4, 5, and 6. Now, BC students, this question right here, number 4, is also on the BC test. So this video will handle your question number 4 as well. So question 4, which is going to be therefore on both tests, question 4 is a differential equations problem. And they tell us we have a potato that we're boiling on a pot on a stove. And when we take the potato off the stove at t equals 0, our potato, we use H for the temperature of the potato, our potato is 91 degrees Celsius. And they tell us that for all time, right, for all time greater than 0, our temperature is always greater than 27 degrees Celsius. So if we read the problem, it says the internal temperature of the potato at time t minutes can be modeled by the function h that satisfies the differential equation. So we have dh dt equals -1/4 times h minus 27. All right, this is Newton's law of cooling. And this tells us this -27 or minus 27, pardon me, the minus of course is part of the formula. The 27 tells me the ambient temperature of the environment is 27 degrees. What does that mean? It means the room is 27 degrees. So our potato, if we leave it in the room, it's going to get down to no less than 27 degrees because the room is 27 degrees. Okay? Now part A says, write the equation of the tangent line, all right? So what do we know the equation of the tangent line is going to be? Well, we have a formula for the equation of the tangent line. And our formula for the equation of the tangent line is our y value, right? In this case, that's h. So our y value minus our functional value. Well, let's go ahead and write this as instead of just as our function. So our functional value at 0, right, at time 0 equals our derivative at time 0 times, pardon me, right, times, yeah, that's right, our derivative at time 0, and this would be x, which for us is going to be 0, right? So this is going to be t, not x, because our variable is t, minus a, and our a is 0. So remember, our general equation looks like this, right? And so what have we gotten here? We have our function is now h. Our function is h. We can see that from here. And we're using t, of course, as our variable. T is our independent variable. And a for us is 0. They want us to evaluate this as 0. So what do we have to find? We have to find h of 0. Of course, we already know that. They gave us that. H of 0, right? They told us h of 0 is 91. And we have to find h prime of 0. Now, we know how to do that. They gave us the derivative already. Right? We get -1/4. We get the temperature at time 0, right? Not 0, h. H goes here, so that's going to be 91 minus 27. 91 minus 27 is 64. A fourth of 64. This turns out to be -16. So now we plug these in, right? So what do we get? We get y minus, right? Minus our temperature at time 0, minus 91, equals our derivative, which is -16 times t minus 0. So we bring the 91 over, and we get y equals -16t plus 91. So in part A, it said find the equation of the tangent line. Done. We got that. Use this equation to approximate the internal temperature when t is 3. So we want to know what is y when t equals 3. Well, that's going to be -16 times 3 plus 91, right? because we're going to plug in 3. And when we plug in 3, we get 16 times 3. 16 times 3 is 48, right? So this is negative 48 plus 91. So our internal temperature is 43 degrees Celsius, approximately 43 degrees Celsius. So that's the answer to part A. Part B says, use the second derivative, right? Use the second derivative to determine whether your answer in part A is an understatement or an overstatement of the internal temperature. So we need the second derivative, right? So before we can begin, we have to find the second derivative. Now they gave us the first derivative, so here, we'll do part B right here. So what is the second derivative? What is the second derivative going to be? Well, it's the derivative of this. Now we all know what this is. This is negative 1/4 h plus 27 over 4. So when we take the derivative of this, we get negative 1/4 h prime. Now, we know h prime, that's the derivative right here. So we get negative 1/4 times negative 1/4, right, times h minus 27. So we get 1 over 16 times h minus 27. Right, that's our second derivative. Now, it told us h is always bigger than 27, right? H is always bigger than 27 degrees Celsius for any time t. For any time t. So what does that mean? Well, if h is always bigger than 27, this would be a number bigger than 27, take away 27. This is positive. We already know 1/16 is positive. So our answer is positive, right? Our answer is positive. Now, what does that mean about our graph? It means our graph is concave up, right? H is concave up. Now, H is the temperature of the potato. So H is concave up, but it's decreasing because our temperature as it sits outside is cooler and cooler and cooler, right? So we used the tangent line, right? We used the tangent line at time 0. So let's put an axis down here. We used the tangent line at time 0. Here's t equals 0. So we took the tangent line here, right? That's the equation we found, the tangent line. We found that equation right here, y equals negative 16t plus 91. We found that tangent line. And then we used that over here at t equals 3. We used the tangent line value to approximate. What they're asking us is, how does that compare to the actual functional value? Well, you can see because we're concave up, right, because we're concave up, our estimated tangent line value is lower than our value on the curve, so our value is an underestimate. 43 degrees Celsius is an underestimate. Okay, an underestimate. Now, part C says, for t less than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g, which satisfies a different differential equation. So apparently when we get down to the first 10 minutes, t is less than 10, right? The t is less than 10, so that's minutes 0 through 10. We actually have a better differential equation that tells us the temperature of our potato. And we need to know if we can find an expression for g of t based on this model, what's the internal temperature. So they want us to solve this differential equation, right? They want us to solve this differential equation. So they give us a differential equation and they ask us if we can solve it. And by solving it, that would give us a function g, and then we plug in 3, and let's see if we get a better estimate. Okay, so I'm going to go ahead and erase this half of the whiteboard. We'll leave this up here so we can see our 43 degrees answer and see if this is a better solution. So now for part C, we have a different differential equation. We have dg dt equals, and we get negative g minus 27, still Newton's law of cooling, but now, it's not technically Newton's law of cooling, pardon me. So we get to the 2/3, and they want us to solve this differential equation. Now this is a separable differential equation. We can solve this, and to solve this, then we would have to separate our variables, so we would get dg divided by g minus 27 to the 2/3 equals negative dt. And remember, we solve a separable differential equation by taking the integral of both sides. So we would integrate this side, and we would integrate this side. Over here, what do we get when we integrate this? We could do a u sub, right? We could do a u sub, but since there's g to the first power here and no coefficient, when you do a u sub with a g to the first and a coefficient of 1, you just get dg equals du. So you can do this just by inspection, just by looking at this. In other words, you can integrate this. And go ahead and, if you want to do the u sub, this is what you would get, right? U equals g minus 27. Du would equal dg. And if we did that, this would be the integral, right? dg is du, so I would have 1 over g minus 27 is u, so I would have u to the 2/3, right? And then I would have a du. When I integrate that, that's u to the minus 2/3 du. I add 1 and divide. So I add 1, that gets me u to the 1/3. I divide by 1/3, that gets me a 3. And look what we end up with. We end up with 3 times. Our u is g minus 27 to the 1/3. So we could have just integrated this and got straight here. Now what do we get on the other side? We get the integral of that, which is going to be minus t plus our constant. Okay. Now where do we go from here? We have to solve for the constant, right? We have to solve for the constant. What do we know that's going to allow us to solve for the constant? Well, we know at the beginning, let's see what they tell us. Okay. So g of 0 is once again 91. So at time 0, our temperature is 91. So if we use that, right, if we use that right here, what are we going to get? We're going to get 3. Our temperature is 91, right? 91 minus 27 to the 1/3 equals negative t, which is 0. Our time here is 0, plus 91. So from here, we get 91 minus 27 is 64. The cube root of 64 is... So we get 91 minus 27 is 64. The cube root of 64 is 4. Is that right? Hold on a sec. I've got a puppy problem I have to go take care of. All right, sorry about that. Like I said, I had a puppy problem I have to take care of. So this isn't 91, right? This is C. All right. So what do we have here now? We have, puppies are distracting. We have 91 minus 27, which is 64. The cube root of 64 is 4. And so 4 times 3 is 12. So we get from here, we get 12 on that side. We get C on this side. So our differential equation, right? We now have, what do we have here? We have 3 times g minus 27 to the 1/3 equals negative t plus 12. So this is our solution to the differential equation. Now, what do we have to do with this, right? We don't have to write it in a neat way or solve it or anything. All they asked us to do is, let's check find an expression for g. So we do have to solve, for g. So now we're going to do some algebra, right? So what are we going to do? We're going to bring the 3 over here, and we're going to get g minus 27 to the 1/3 equals negative t plus 12 divided by 3. We're going to cube both sides to get g minus 27 equals negative t plus 12 over 3 cubed. And now we're going to move the 27 over, and we get g of t equals negative t plus 12 over 3 cubed plus 27. And now the very last thing they asked us to do is use this, right? Use this to find the temperature at time t is 3. So if we're going to do that, we're going to plug back in 3, right? So from here, we have to find g of 3. Now what do we get? Let's see, we get 3 here. So time is 3, so 3 minus negative 3 plus 12 is 9. 9 divided by 3 is 3. 3 cubed, 27. 27 plus 27 is 54 degrees Celsius. So our better model, the one we used in part C, our better model comes up with 54 degrees Celsius. Our not quite as accurate model, which we thought in part B underestimated, said 43 degrees, which is well below 54 degrees. So that confirms what we found in part B. All right, so for those of you doing the BC test, this was your number 4. You can go ahead and close out this video at this point and turn on the video for your AP Calc BC free response, and of course that'll be problems 5 and 6 only. For you taking the AB test, don't do anything because I'm going to erase and we're going to start problem number 5 right now. All right, so let's see, what does problem number 5 say? Problem number 5 says 2 particles move along the x-axis. For time between 0 and 8, the position of particle P at time t is given by, and they give us a position function, the natural log of t squared minus 2t plus 10. Okay. So, and then it says the velocity is given by v of t equals, oh, this is a separate particle. I'm sorry, this is particle q. We have particle q and we have the velocity function. So we have 2 particles. Let's go ahead and write this up right now. Number 5, we have 2 particles and they're moving along. So we have particle P. So what do we know about particle P? We know its position, right? Its position at time t is given by the natural log of t squared minus 2t plus 10. Okay, so that's what we know about particle P. Then we have particle Q. Now, what do we know about particle Q? We don't know its position. We know its velocity. We know its velocity. And its velocity is given by t squared minus 8t plus 15. Now, we don't know where particle P is. They don't tell us any information about that. But another piece of information they give us about particle Q is they tell us that when t equals 0, that its position, now this is particle Q's position, particle Q's position at time 0 is equal to 5. All right, now don't think that means when we put a 0 up here we get a 5. That's particle P's position. We only have particle Q's initial position. Now it says in part A, when is particle P moving to the left? When is it moving to the left? All right, so if we draw here's part A. when is P moving left? Now remember, this is on the interval 0 to 8, right? Because that's all we know. This is all true between 0 and 8 up here. So when is particle P moving to the left? That's what they want to know. Well, what do we need to know if it's moving to the left? We need to know its velocity, right? Because if it's moving left, here's a number line. We don't know where particle P is. Let's just say this is particle P. If it's moving left, that means its velocity is negative because it's going to the left. So we need, right, we want to find V of particle P. Now, we don't know V of particle P. They didn't tell us V of particle P. They told us the velocity of particle Q, but they asked us about particle P, so we're going to have to find V. Now, we know velocity of particle P is equal to the derivative of the position of particle P. And we can find that. We can take that derivative. It's the derivative of a log, so that's going to be 1 over t squared minus 2t plus 10 times the derivative of what's inside, which is 2t minus 2. All right? Now, what do we have to do? We've got to determine when is this derivative equal to 0, and when does this derivative fail to exist? Right? When does it equal 0, and when does it fail to exist? Now, let's take a quick look at the discriminant down here, right, to see if this has any solutions. If we look at the discriminant for this piece right here, remember, that's b squared minus 4ac, right? We get b squared, which is going to be 4, minus 4 times a, which is 1, times c, which is 10. That's less than 0. So this has no solutions. So we do not have to check to determine when this fails to exist. This never fails to exist. If we were to graph this parabola, it opens up and it never touches the x-axis. So our only critical number is 2t minus 2 equals 0, or t equals 1, right? T equals 1. Now, what do we have to do? Well, we got to do the sine test. So here's our sine test. Here's 1. Now remember, our sine test stops at 8 and stops at 0. So we need to run the sine test. We have the derivative, right? The derivative is right here. So we can, well, let me move that down. I didn't leave a lot of room for the sine test there. So let's just slide that down. Here's 1, here's 0, here's 8. So those aren't really arrows, those are really ends. What are our terms? We have 2 times t minus 1, and then we have t squared minus 2t plus 10, which we've already figured out is a parabola that opens up, so it's always positive. And it's a parabola that opens up and is above the x-axis. It has no x-intercepts. So what about this? We plug a number in below 1, like a half. This is going to be negative. We plug a number in bigger than 1, like, it can't be 1,000,000 because it's got to be less than 8. So we plug in 6 and we get a plus. So our derivative, right, our derivative, which is velocity of particle P, our derivative is negative here, positive there. So what does that tell us? Well, that tells us the particle is moving to the left over here, right, over here. So our particle is moving left between, let's start up here. Now, is it moving left at time 0? We need to find out, right? Notice I made it closed because I already did the math in my head. If I put 0 in here, what happens, right? This is my velocity function. If I put 0 in here, I get negative 2, right? 2 times 0, negative 2. On the bottom, I get positive 10. Negative 2 divided by 10 is negative. So it's moving left at time 0 as well. That's why I have it closed there. So we got to check the endpoints. It's not moving left at time 1. We know at time 1 our velocity equals 0. Okay? So that's part A. Part B, it says, when are the two particles moving in the same direction? Right? When are they moving in the same direction? So right now, what do we know about particle P? Right? Right now, if we had to write about particle P, this is 8, this is 0, here's 1. We know our particle P is moving left here, and it's moving right here. That's what we know, right? We just figured that out. Now, what about particle Q? Right? What about particle Q? Well, let's change colors, and we'll do particle Q in another question. We know the velocity of particle Q. They gave us that. And it's equal to t squared minus 8t plus 15. We don't have to take the derivative and do the sine test. We already have the derivative. We already have its velocity. This factors, right? This is t minus 3 times t minus 5. So if we take this, we don't have to take its derivative, but if we do the sine test, right? If we do the sine test, we have two terms, t minus 3, t minus 5. So we have two zeros. Now remember, we started 0, we ended 8, we have 3, and we have 5. I need a number. This is my velocity, so this is my derivative. Remember, velocity is the derivative of position of Q. So it's going to tell me when it's moving right, when it's moving left. So I need a number to plug in here. So I plug in 2. I get 2 minus 3, that's negative. I plug in 2 here, I get another negative. Here I plug in 4. 4 minus 3 is positive. Here I plug in 4, I get a negative. Here I plug in 6. 6 minus 3 is positive. 6 minus 5 is positive. So here we're plus, here we're minus, here we're plus. What does that mean? This means we're moving right. This means we're moving left. Velocity is negative. Here we're moving right. Now they want to know, when are we moving the same direction, right? When are we moving in the same direction? So we can look at our number line here and our number line up here and determine when we're moving in the same direction. So when will that be? It'll be whenever this is going the same as this. So what about between 0 and 1? Between 0 and 1 up here, particle, now here, remember, this is particle P, right? This is particle P up here, and this is particle Q down here. So between 0 and 1, particle P is moving left, but between 0 and 1, right, between 0 and 1 down here, particle Q is moving to the right. So they're not moving at the same direction. Now, from 1 on, particle P is moving right. So once we get past 1, right here, which I made is blue, particle P is moving to the right. So we're the same, right? We're the same here, and we're the same here. We're moving to the right at both of those times, right? Now, so when are we moving at the same? This is 1. Particle P starts moving to the right at 1. We started moving to the right at 0. So right here we get 1 to 3. Now, we're not moving in the same direction at 1, are we? We'll go back and talk about that. We'll go back and talk about it. And then what about and, right? And 5 to 8. We gotta ask ourselves, are we moving in the same direction at both of these times? Well, at time 1, particle P is stopped, right? That was our 0. So particle P is stopped. Its velocity is 0. But at time 1, 1 is in this interval right here. At time 1, particle Q is moving to the right, so they don't match there. At time 3, particle Q is stopped. But at time 3, particle P is moving to the right, so they're not moving at the same time there, same direction. At 5, we're stopped for particle Q, but we're moving for particle P, not moving in the same direction. what's going on at 8? Well, if I put 8 in here, that's 2 times 8, 16, minus 2, 14. This is positive, 14 over 14. So at time 8, particle P is moving to the right because its velocity is positive. At time 8, this particle, this would be 8 minus 3, that's positive. This would be 8 minus 5, that's positive. So they're both moving to the right at time 8. So we have to make sure we get that included. They're both moving to the right at time 8. All right? Now, part C says, find the acceleration of particle Q at time 2. Is the particle increasing or decreasing? So we're working with particle Q. We need acceleration. So we'll stay, this is part C. Since we're working with particle Q, we started it in black, we'll stay in black. The acceleration of particle Q, of course, is its derivative of velocity. So the acceleration of particle Q is the derivative of the velocity of particle Q. Now we know the velocity of particle Q, they gave us that. So the derivative of that's pretty nice. That's 2t minus 8, which is 2 times t minus 4. And they've asked us specifically to find the acceleration at time t is 2. So acceleration at time 2 is 2 minus 4, it's negative 2, right? Times 2, we get negative 4. So our acceleration at time 2 is negative. Now it says, is the speed of the particle increasing or decreasing? Well, what do we know? From here, we know at 2, right? Let's just write a summary. At t equals 2. We'll write a summary. Our acceleration is less than 0. It's negative. Our velocity, if we look up here, t is 2 is right here. Our velocity is greater than 0, right? Greater than 0. So what's happening? Our particle is moving this way, but its acceleration is going in the opposite way. So it's braking. Its acceleration is going opposite of its velocity. So since acceleration and velocity are opposite in sign, we know velocity is decreasing. Right? Velocity is decreasing. And we need to explain our reasoning, and so we would say velocity is decreasing because velocity and acceleration have the opposite signs. Okay? Now, part D says, find the position of particle Q the first time it changes direction. All right? Well, if we go back to our picture, the first time we changed direction is right here at t is 3. Right? That's the first time we changed direction. We didn't change direction any place other than that. Well, I mean, that's the first time we changed direction at 5 as well, but we were moving right and then we started moving left. So t is 3 is our magic place. So let me clear some room over here. I'll go ahead and erase this part. Now, they want us to tell them what's our position when t equals 3. Right? Well, if we look at what we were given for particle Q, we were given its position when t equaled 0. Right? We knew at time 0, our particle was at number 5. It was at place 5. So, first of all, for part D, oh, here, we're working with particle Q. Stay with black. T equals 3 is the first time we change direction. So we want to find the position of particle Q at 3. That's what we want to find. And we don't know what that is. We don't know. But we know the position of particle Q at time 0. We know where we are at 0. So if I were to integrate between 0 and 3, the velocity I would get the antiderivative of velocity at 3. The antiderivative of velocity at 3 is position at 3. That's what they asked me to find. Minus the antiderivative of velocity at 0. I know that. This is fine. They told me that. I can find this. We can all do the integral of that. This integral turns out to be the integral from 0 to 3 of t squared minus 8t plus 15 dt. We can all find that. We integrate that, we get t cubed over 3 minus 8t squared over 2 plus 15t evaluated between 0 and 3. And what does that turn out to be? Let's see. At 3, that turns out to be 27 over 3, that's 9. That's 9 times 8, 72, right? 72. Divided by 2, that's minus 36. And that's plus 45. So what do we get here? We get 45 minus 36, which is 9. Plus 9, we get 18. So if we go back to our fundamental theorem of calculus part 2, right? This question turned out, this is the net change theorem, right? We've seen this so many times before. This is the net change theorem. It says, if I integrate a derivative, I get the antiderivative back. So what do we know here? We can plug our numbers in. This side is 18. We just found that integral right here. This side is 5, right? They told us that. So we know the position at time 3, right? X sub q at time 3. We're going to bring the negative 5 over here, and we're going to get this is equal to 23. So our position at time 3 is 23, all right? So that completes question number 5. And now let me clean the board off, and we'll do question 6. All right, so let's work on question 6. So question 6, they give us a function f of x. And they actually give us a formula for this. They tell us it's cosine of 2x plus e to the sine of x. Now there are two other functions given in the problem as well. Function g, which all we have there is a table of values. And then function h, and all we have there is a graph. Right? So they give us these functions, and they ask us questions about relationships between these functions. So in part A says, find the slope of the tangent line to the graph of f. So we want the slope of the tangent line. Well, that's a derivative. So we want to find f prime of x. Well, we can all take the derivative of cosine. We get negative sine of 2x times the chain rule. The derivative of what's inside is 2. The derivative of e to the sine x is, of course, e to the sine x times the derivative of sine, which is cosine. Now they want us to find f prime at pi. Well, that's nice. So this is minus the sine of 2 pi times 2 plus e to the sine of pi times the cosine of pi, right? And if we draw a quick graph, just to remind everybody, sine goes like this. So sine of pi is 0. Cosine goes like this. Cosine of pi is negative 1. So this is 0 times 2, that's 0. This is e to the 0, that's 1. Cosine of this, so we get 1 times negative 1, so we get negative 1. All right, so the answer to part A is -1. Now part B says, let k be a function. So k is going to equal the function which is h of f of x. So k is a composite function, right? It's a composition of these two. And they want us to find k prime of pi. So we have to find k prime. K prime is the derivative of this. Now this is the chain rule, so that's h prime of f of x times the derivative of what's inside, f prime of x. So they want us to find k prime of pi. So that's h prime of f of pi, right, times f prime of pi. Now we found f prime of pi right here. We know that's -1. We need f of pi. Okay, well we can find f of pi. F of pi is up here. So let's find f of pi. So that's going to be cosine of 2 pi, right? 2 pi plus e to the sine of pi. Just plugging in pi into my function for f. Now what do I get there? I get cosine of 2 pi. Cosine of 2 pi is 1. I get sine of 1 pi, right? Sine of pi is 0. So this is 1 plus 1. This is going to equal 2. So what do we get? Going back here now, we have k prime of pi equals h prime of 2, right? Because f of pi was 2, times f prime of pi, which we said was -1. So now where am I going to go to find h prime of 2? I'm going to look on my graph, right? On my graph, right here. H prime of 2, 2 is right there. Oh, that's -2. 2 is there. So h prime is the slope of that. Change in y over change in x is 3, right? Change in y is 1. Change in x is 3, and it's negative. So h prime of 2 is going to be -1/3 times -1 then, and that gets us +1/3 for k prime of pi. Now part C says, let m, oh my goodness, so now we get another function. Part C, m of x is equal to g of -2x times h of x. And they want us to find m prime at 2. So we have to find m prime. Now this is a product, so m prime of x, we're going to have to do the product rule here. So that's going to be the derivative of the first one, that's g prime of -2x, times the derivative of what's inside, don't forget that, -2, times h of x, plus, to finish out the product rule, we get g, right, of -2x, times the derivative of that, which is h prime of x. Now, they asked us to find m prime of 2. So what does that look like when we get all done here? That looks like g prime, x is 2, so that's g prime of 4 times -2 times h of 2 plus g of, right, g, x is 2, so that's g of, oh, I'm so sorry, that's going to be g of -4, right? So this is supposed to be a -4 right here, isn't it? There we go. And now that's going to be h prime of 2. Plugging everybody in. So we get g prime of -4 times -2 times h of 2 plus g of -4 times h prime of 2. Now we have to find all of these. Do we know g prime? Well, we have a table. Do we know g prime of -4? We do. It's -1. So we're going to read that off the table. Don't forget your -2 here. Do we know h of 2? Well, we can look over here, right? This is our graph of h, right? This is our graph of h. So we're going to look over here at h of 2. Now, how are we going to find h of 2, right? How do you know where that dot is? On your graph, you know the slope. We decided the slope was negative 1/3 right there. So if the slope is negative 1/3, then that point is negative 2/3, right? From algebra 1. So that's negative 2/3. You don't just guess at that. You know 2 points, you can find the equation of the line. You know it goes through 0, 0, and it goes through 3, 1. You can find the equation of the line, plug in 2, and you get negative 2/3. What's g of negative 4? Well, g of negative 4 is on our table. That's 5. H prime of 2. Well, we already found h prime of 2, right? We did h prime of 2 right here, and we said h prime of 2 was negative 1/3. So what do we get here? We get negative, 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 so that's negative 4/3. And here we get negative 5/3. So we get negative 9/3, which is negative 3. So m prime of negative 2 is negative 3. So they're really making us play with the quotient, the product rule and the chain rule on this problem. D says, is there a number in the closed interval negative 5 to negative 3 such that g prime of c equals negative 4? Justify your answer. So when I look up here at my function, it says, here's g is differentiable, all right? So let's clear some space over here. So, part D says, is there a number in the closed interval from negative 5 to negative 3 where g prime equals negative 4? Well, what do we know about g? If we take a look at g, we know at negative 5, we're over here, aren't we? At negative 5, we know g is 10. So we're up here at 10. So this is negative 5, 10. And we know at negative 3, g is 2. So what do we know? We know our function is differentiable, so therefore it's continuous. They told us that. They said g is differentiable. G is differentiable, therefore g is continuous. So what do we know about our function? We know our function goes from here to there, right? It goes from here to there, continuously. So it could be this. It could, right? That works. There are other choices, right? Our function can go like this. We don't know what our function looks like. The question is, does the derivative equal negative 4? All right, does the derivative equal negative 4? Well, what's the slope between those 2 points? All right? What's the slope between those 2 points? The slope is going to be change in y, so that's 10 minus 2 over negative 5 minus 3. So that's 8, right? That's 8. Divided by, this turns out to be negative 2, so that's negative 4. So, what does that tell me? How do I know the answer? Well, the question is all about the mean value theorem, right? The mean value theorem, remember, says if the function is continuous between these 2 points, then there has to be a place where the slope of the derivative equals the slope of the secant line. There has to be. We just found the slope of the secant line. So there has to be a point by the mean value theorem where the slope of the derivative equals the slope of the secant line. Now, I don't know what that value is, but somewhere between, because it's the mean value theorem, between -5 and -3, we do have that point by the mean value theorem. All right, that finishes up questions 4, 5, and 6. My next video will be about the 2019 AP exam.